Hey everyone! Welcome to the episode The EUV Mirror, the tiny thing that makes your phone faster every year. If you've ever wondered, why does every new smartphone feel so much faster? Why is AI getting smarter so quickly, yet the chips aren't getting physically bigger? Part of the answer is one very small, very special mirror that humans had to build to near perfect precision. Let's make it super simple. We want computer chips to keep getting smaller every year. That's Moore's law. Smaller chips equals faster, more powerful, use less battery. To make them smaller, we print tiny patterns onto a silicon wafer using light, like projecting a super detailed photo onto paper. But the light we've used for years, deep ultraviolet, 193 nanometers wavelength, is no longer short enough. It's like trying to write tiny letters with a thick marker. You can't get sharp edges anymore. So we had to switch to even shorter light, electreme ultraviolet, or EUV, at just 13.5 nanometers. That's shorter than the length of a water molecule several times over. Here's the crazy problem. EUV light gets absorbed by almost everything. Air absorbs it completely. Normal glass absorbs it completely, so regular lenses don't work. A single layer of metal reflects only 0.5 to 1%. The rest turns into heat. If we used the old way, the light would disappear before it even reached the chip. The whole tech world would stall. No faster phones, no better AI, no progress. The only way forward? Use mirrors to reflect the light instead of lenses. But not normal mirrors. These mirrors have to reflect EUV light well enough to project razor-sharp patterns smaller than 1,000th of a hair onto the silicon. So how do you make a mirror that reflects something almost nothing reflects? We don't use a regular mirror. We build a layer cake mirror called a multi-layer mirror. We stack dozens of super thin layers, alternating two materials: molybdenum, Mo, a hard metal that reflects well; silicon, Si, a thin spacer that lets light pass through to the next layer. Each layer is only 3 to 4 nanometers thick, 1,000,000 times thinner than a human hair. We stack about 50 to 70 pairs, hundreds of layers total. The trick is simple. When the layers are exactly the right thickness, the light waves bouncing off each layer team up and reinforce each other, like singers harmonizing to make the sound louder. If everything is perfect, we can get up to approximately 70% reflection, which is amazing for EUV light, but that's still not enough. The surface has to be atom-level smooth. It's not just about reflecting well. The projected image on the chip has to be perfectly sharp. If the mirror surface has even one tiny bump the size of a single atom, 0.2 to 0.3 nanometers, the image blurs like taking a photo with a scratched lens. So the mirror must be insanely smooth. Here's the mind-blowing comparison. If we blew this mirror up to the size of Germany, the tallest hill or deepest pit on its surface would be only 0.1 millimeters high, about the thickness of a very thin human hair. That means we have to polish the mirror at the atomic level. We use a machine that shoots ions to knock atoms off one by one, called ion beam figuring, then measure it with tools so precise it feels almost like magic.
Why is heat such a big enemy? The mirror absorbs about 30% of the EUV light and turns it into heat. Even a tiny temperature change can make the mirror warp slightly, and that ruins the focus. That's why the base material has to be special ultra-low expansion glass that barely changes size when it gets hot. And everything happens in a perfect vacuum because air would eat the EUV light. So in short, the EUV mirror is the most perfect thing humans have ever built because it must reflect light that almost everything absorbs, be smooth to the level of atoms, expanded to country size. Highest bump is 0.1 millimeters, and have hundreds of layers, each only a few atoms thick. Because of this one mirror, chips keep getting smaller, faster, more efficient, which is why we have today's powerful AI, flagship phones, and everything else. It's humans fighting physics and somehow winning inch by inch with insane patience and crazy technology.
Today, we go back in time. How did anyone even attempt to build something this crazy? And how did it go from a few scientists in labs in the 1970s to the only mirrors powerful enough to make the chips inside your phone right now? Let's start in the early 1970s. Back then, people already knew that shorter wavelengths could print smaller patterns on chips. X-rays were one idea, but they were too hard to control. Then, a researcher at IBM named Eberhard Spiller got interested in something called multilayer coatings, basically stacking thin films to make better mirrors for very short wavelengths. In 1971, Spiller used a computer to simulate what would happen if you stacked just a few layers of different materials. The math looked promising. So he actually built a small mirror with only 6 layers using magnesium fluoride and gold. It wasn't great, but it reflected a tiny bit more than a single layer would. That was the first proof multi-layer mirrors for extreme short wavelengths could actually work. A few years later, in 1978, Spiller met Troy Barbee at Lawrence Livermore National Lab. Barbee had invented a new way to deposit those thin layers called magnetron sputtering. It's like sandblasting atoms in a vacuum chamber so they land perfectly flat on the surface. With this technique, they could control thickness down to fractions of a nanometer. Suddenly, reflectivity jumped. They hit over 60% reflection in some tests. That was huge. For the first time, people started believing EUV mirrors weren't just theory. Meanwhile, in Japan, a researcher named Hiroo Kinoshita at NTT also experimented with EUV for chip making. He saw Spiller and Barbee's work and realized reflection optics could be the way forward for lithography. In the late 1980s and early 1990s, Japan invested heavily. They built prototype EUV systems and started making their own multilayer mirrors using molybdenum and silicon, the exact pair we still use today. But building one good mirror in a lab is one thing. Making many of them, perfectly curved, large enough, hundreds of millimeters wide, and consistent enough for real chip factories, that's a completely different problem. By the mid-1990s, the big players got involved. In the United States, a group called the EUV LLC, a partnership between Intel, AMD, Motorola, and the Department of Energy Labs, was formed to push the technology. They worked with a company called Tinsley Laboratories, later part of SVG, to polish the mirror substrates to incredible precision. They used special glass called ULE, a type of fused silica mixed with titanium, so it barely expands when heated. Then they polished it using computers and ion beams to remove atoms one layer at a time.
But even with all that, the mirrors still had tiny imperfections, mid-frequency roughness that scattered light and reduced contrast. It took years of tiny improvements, from 0.2 nanometers roughness in 2005 prototypes down to 0.15 nanometers in 2007, and finally around 0.05 nanometers by 2011. No big eureka moment, just relentless, boring, expensive tweaking. Around the same time, a quiet but massive shift happened in Europe. ASML, the Dutch company that already made the world's best lithography machines, wanted to buy the American optics company SVG, which owned Tinsley. But the US government blocked parts of the deal for national security reasons. They didn't want advanced optics tech leaving the country. So ASML had to sell off the EUV optics division. That's when Carl Zeiss SMT from Germany stepped in. Zeiss is famous for making the lenses in high-end cameras and microscopes. In 2001-2002, they took over the EUV mirror project and basically became the only company in the world that can make these mirrors at production quality today. Zeiss didn't invent the multilayer idea, but they perfected the manufacturing. They built giant vacuum chambers for deposition, ultra-precise polishing machines, and metrology tools that measure surface errors down to picometers, trillionths of a meter. They also developed ways to fix tiny defects after deposition, using the same ion beams to shave off problem areas atom by atom. By the late 2000s and early 2010s, Zeiss mirrors were good enough that the full EUV system could finally work. In theory. But here's the twist we'll save most of for episode 3. Even with perfect mirrors, the machines still couldn't produce chips fast enough. The real bottleneck turned out to be the light source itself, generating enough EUV power without melting everything. ASML eventually spent billions to buy the American company Cymer in 2012 to fix that problem. But that's the next chapter. For now, the key takeaway from this episode, the EUV mirror didn't come from one genius inventor or one dramatic breakthrough. It came from 40-plus years of quiet, stubborn work across labs in the US, Japan, and Germany. From Spiller's 6-layer experiment in 1971 to Barbie's sputtering in 1978 to Kinoshida's prototypes in the 90s to Zeiss turning it into factory-grade hardware in the 2000s and 2010s. It's a story of international teamwork, insane precision, and never giving up when almost everyone said it was impossible.
By around 2010-2011, the mirrors were finally good enough. Zeiss had nailed the multi-layer deposition, the ultra-precise polishing, the ion beam figuring, and the picometer level metrology. Wavefront errors were down to the required fractions of a wavelength. In theory, you could project patterns smaller than 10 nanometers with almost no blur. But when ASML put those mirrors into full prototype EUV machines, like the NXE 3100 and later models, something was still terribly wrong. The machines were slow, painfully slow. Even with perfect optics, the throughput, how many wafers you can process per hour, was way too low for real factories. A modern chip factory needs to produce hundreds or thousands of wafers a day. These early EUV tools were doing maybe a handful. Why? Because the light source wasn't bright enough. EUV light at 13.5 nanometers doesn't exist in nature in usable amounts. You have to create it artificially. The method chosen was laser-produced plasma. Fire a powerful CO2 laser at tiny droplets of molten tin falling at high speed, like shooting bullets at raindrops. When the laser hits the tin droplet, it explodes into super hot plasma that emits a burst of EUV light right at 13.5 nanometers. Sounds cool, right? But in practice, it was a nightmare. The tin droplets had to be perfectly uniform and perfectly timed, hundreds of thousands per second. The laser had to hit each one dead center with insane precision. The plasma emits EUV in all directions. Only a tiny fraction gets collected by the mirrors. The collector mirrors, also multi-layer, get coated with tin debris and degrade fast. Power output was stuck at a few watts for years, while factories needed 250 plus watts to be economical. This was the real bottleneck, not the mirrors anymore. The optics were ready, but there wasn't enough light to expose wafers quickly. Everyone in the industry was frustrated. Some even said EUV might never make it to high-volume manufacturing. ASML had been patient for a long time, collaborating with Cymer, the American company making the light source tech, since the 2000s. But by 2012, they couldn't wait anymore. They decided to buy Cymer outright for about 2 billion euros, around $2.5 billion at the time. It was one of the biggest bets in semiconductor history. ASML basically said, if we're going to make this work, we need full control of the source too. After the acquisition, things accelerated dramatically. They improved the tin droplet generator, upgraded the CO2 lasers to multi-kilowatt power, developed better debris mitigation using hydrogen gas to clean tin off mirrors, and optimized the collector optics. By the mid-2010s, inline EUV power reached 100 plus watts, then 200 plus watts, and eventually over 250 watts in production tools like the NXE 3400 and NXE 3600 series. With enough light, plus Zeiss mirrors, plus improved stages and metrology, throughput finally crossed the threshold. By 2018-2019, major foundries like TSMC and Samsung started inserting EUV into real production lines for 7 nanometers, then 5 nanometers, 3 nanometers, and now 2 nanometers class nodes. Today, 2025-2026, almost every cutting-edge chip, Apple M series, Qualcomm Snapdragon, NVIDIA GPUs for AI, AMD Ryzen, Google Tensor, and more, is made using EUV lithography. Without these mirrors and the full system, we wouldn't have the density, efficiency, or performance needed for today's AI boom. The models running ChatGPT, image generators, self-driving tech, they all depend on chips printed with EUV. So what's the big takeaway from this whole 3-episode journey? The EUV mirror isn't just a piece of glass. It's the symbol of how far humans will go when physics says no more. Decades of quiet, stubborn engineering across countries, billions of dollars, thousands of PhDs, endless failed prototypes. No single hero, just teams refusing to quit. Spiller and Barbie in the 70s, Kinoshita in Japan, Zeiss in Germany, ASML and Cymer in the endgame. It reminds us that the tech we take for granted, the phone in your pocket, the AI answering your questions, didn't appear by magic. It was built, layer after atomic layer, against impossible odds. And the story isn't over. We're already pushing toward high-NA EUV, even bigger mirrors, even shorter effective wavelengths, for sub-2 nanometers nodes. The next generation of mirrors is already in development. Thanks so much for joining me through all 3 episodes. If this series opened your eyes to how wild modern chip making really is, please drop a like, subscribe if you haven't, and leave a comment. Maybe share which part surprised you the most or what tech topic you want next. Until the next deep dive story, take care, and I'll see you soon.